In this video, we're going to talk about integration by parts. We're going to look at a couple of examples, and we're also going to look at the proof of why this works. It's kind of a hard beginning. It's kind of a hard setup. It's really not, but it looks like it will be. Essentially, we have two functions, okay, u and dv. We have two functions that are a product in an integral. We name one of them u and one of them dv. So it's just a product of two functions, and we pick which one serves as u and which one is dv. Now the whole purpose of this is that if we kind of reversed which one was u and which one was dv, and by reverse I mean instead of u we have du, instead of dv we have v. So if you kind of said, well, if I had the derivative of one and the integral of the other, that would make for a much easier integral. That's what we're trying to do. And again, it seems like that would be hard to do, but it's really not. It's really not that bad. I'm going to show you an example, and then we're going to look at the proof, and I think you'll see it really isn't that bad or hard to pick. Okay, so in this first example, we've got x multiplied by cosine of x. So again, see that it is a product. Okay, we've got an x multiplied by a cosine x. So here's this. Now, if you think, well, okay, I have to pick one to be u and one to be dv. So I'm going to write u equals. Now, I'm going to put a little star by this, and I won't do that in many videos, but this is the first time you're seeing it. And then I'm going to write du underneath it. Over here, I'm going to write v and dv. And again, I'm going to put a little star by dv because this is what we are going to pick. We're going to pick one function to be u and the other function to be dv. Okay, so we need to pick one that if we found the derivative of it, it would make our life a lot easier. That's going to be our u. I'm going to start by picking x, okay? And I think you'll see why here in a minute. So if I pick x to be du, if this is my u, then the rest of it is dv. So cosine x dx. Because you should be taking up everything. So you see, all right, if this is u, then the rest of it needs to be dv. So u dv. Then I fill in the blanks. The derivative of u is the derivative of x is 1 dx. And I have dv, I want the antiderivative, so that's sine. Okay. Now, I always pick it like this. I say, well, it looks like a 7. All right? The formula. It says the original integral is equal to u times v, x multiplied by sine of x, minus the integral of v times du. Well, sine x times 1 dx, oh, and I shouldn't have put a dx there, I'm sorry. Sine times 1 dx is sine dx. Well, now just think about this. What is the antiderivative of sine? It's negative cosine. So I have x sine x minus negative cosine. I should put a plus c there. So x sine x plus cosine x plus c. And there is my antiderivative. Now this always looks a little tricky, and people usually look at this and think, well, how did I end up with such a big function with all these terms? Let's just find the derivative of this for a second. I'm just going to put derivative right there. I'm just going to put the derivative. So of this thing I put in the box. First times derivative of the second plus second times derivative of the first. And then I need to find the derivative of cosine. The derivative of cosine is negative sine. And the derivative of a constant is 0. Well, look what happens to these signs. And it leaves me with x cosine x, which is what I started with. And of course, if I find the integral and then find the derivative, I should end up where I started with. So this is just kind of verification that it worked. The black box, that's the actual answer. Now, I think this brings up a point, though, a fair point of, well, okay, you picked u to be x, and that worked out really well. What if you didn't do that? What if you said, no, u is cosine, and du then, the derivative of cosine is negative sine. Okay, so remember, we pick u and dv. So if u was cosine, that meant dv was x. So the antiderivative is that. So when I do my magic 7 here, I get 1/2 x squared cosine x minus negative 1/2 x squared sine x dx. And you look at this and you say, well, that really didn't help. And I agree. This integral is even more complicated than the integral we started with. All our work's correct. The integration by parts is correct. But we ended up with something that was even harder than what we began with. So this isn't the correct substitution. Okay, so I'm just going to put an X through this. So you have to be careful when you pick your u and dv that it actually is going to move you in the right direction to what you want to accomplish, which is an easier integral. Okay, you want this integral right here to be something simple that you can integrate. That's what you want to move to. Okay, so you got to be careful with what your substitution really is. Let's look at the proof. So this is the proof of integration by parts. What I've stated here right at the beginning is that if I take the derivative of a product, so two functions multiplied together, I do the first multiplied by the derivative of the second, plus second multiplied by derivative of the first. So this is just product rule. Then I found the integral of each term. Integrals are algebraic. If I integrate one side, I have to integrate the other. So you can see I just did the integral. And integrating this side, you can split by addition and do the integral of each term. Well, by fundamental theorem of calculus, the integral of the derivative is just uv. And I think now you can see how you can manipulate this to be the formula you want. Okay, so it really is just doing product rule and then integrating product rule. All right, in the next video, I'll do a couple more examples of integration by parts, including the shortcut that is in the movie Stand and Deliver that he refers to as tic-tac-toe method. So look there for some more examples.